This week, we covered the mean value theorem, and we used that we used that to get several results which allow us to use calculus to sketch the graph of a curve. On this worksheet, the first two questions are mean value theorem questions, then we have some graphing questions. So remember, the mean value theorem says for a continuous function which is differentiable, so it doesn't have any corners or cusps, if you take a line through 2 points, then somewhere between them, you're going to have a tangent line that's parallel. And we can interpret the slope of this tangent line using derivative, and we can interpret the slope of this line just using the change in y over change in x. So we have two parallel lines, so they have the same slope. The slope of this one, well, the slope of the lower one, change in y, divided by the change in x. And then the mean value theorem says if it's continuous and differentiable, you will be able to find a c value in the middle at which, well, for which the tangent line is parallel to this line. And the tangent line at c is given by f prime of c. I personally find this equation a little hard to purely memorize with all the letters and derivatives, but I always find it much easier to just draw the two lines and then write out the slope of the two lines. And 1 and 2 deal with this theorem, so let's do number 1. Number 1, for this function, show there is no c value with f prime at c equal to f of 1 minus f of negative 1 over 2. So we're going to show that no c value satisfies this equation. What does the right side of this equation equal? Well, f of 1 over 1 is 1. F of negative 1, 1 over negative 1 is negative 1. So on the top, we have 1 minus a negative 1. Sorry, a chair was in my way. Over 2. So we have 2 over 2, which is 1. So we're going to show that there's no c value where f prime of c equals 1. Well, we need f prime. Derivative. So you could write negative 1x to the negative 2. I'll just jump to the fractional form. F prime x is negative 1 over x squared. So here, f prime at c would be negative 1 over c squared. So to answer the question, show there's no c value, I'll say such a c value would satisfy. What would it satisfy? Well, f prime of c, negative 1 over c squared equals 1. If a c existed, it would satisfy this equation. C squared equals negative 1. And that has no real solution. We are not doing anything with the complex numbers. Complex, another word for imaginary numbers. Only real numbers. So there is no such c value. Any questions about, well, really number 1 has 2 different things to do. This is the first part. Now, any questions about what we did here? So we needed to show no c value exists. And we arrived at that because we can't solve that for c. Now, the mean value theorem, if it applied, would have guaranteed a c value exists. So right here, no c value exists. Therefore, the mean value theorem doesn't apply. In this case, on the interval -1 to 1. So the second part of this says, why doesn't the mean value theorem apply to this function on that interval? Well, there are two assumptions for the mean value theorem. One or both of them mustn't work. So let's take this function. We need it to be continuous and differentiable. Was there a question? Okay. So we're going to take this function. If it applied, it would need to be continuous and differentiable on -1 to 1. Here's 1 over x, and this function is not continuous at 0. Also not differentiable, but we only need 1. So is not continuous at x equals 0. So the mean value theorem, MVT, doesn't apply to f of x on -1 to 1. It's also not differential. You could say it's not differentiable at x equals 0, but I'll just say not continuous, so it doesn't apply. Notice if we took like the interval 1 to 3, it would apply, but it wouldn't apply on -1 to 1. So any questions about number 1? Okay, so this is one type of mean value theorem problem that we could see. Another is like number 2, and I'll show two different solutions for number 2, two different ways to arrive at the solution. So number 2 says, maybe I'll read it. Let f be a continuous function, okay? If f of 1 equals 2. I'm going to draw this pretty large. Is this marker? Yeah, that is showing up. You know, sometimes it's hard to tell if the marker is showing up on a camera because it looks like it's dying right in front of me, but it looks like it's showing up fine on the computer. So f of 1 equals 2. So here's 1, here's 2. F prime is between 1 and 4 on the interval 1 to 6. So 6 will be relevant. Then what are the maximum and minimum values f of 6 can be? And try finding bounds for f of 6 by graphing and starting at 1. So that hint applies to the first way we'll do this. The second way doesn't require a graph. I personally like the graph way. In my mind, it takes less thinking. The other one has equations to work with. So we have that the derivative on 1 to 6 is between 1 and 4. So that means slopes of tangent lines are at a minimum 1 on this interval 1 to 6, which means if we take this line, let's say that line has slope 1, and we go through this point. Well, whatever this function is, it's continuous, is going to go through this point, but it can never go below this line. If it did go below this line, there are a few different ways it could go under the line. But one of them, let's just say it goes like this. Well, on all of these points, f prime would be between 1 and 4. But tangent lines here, for example, are going to be, well, they'll be a negative slope, but in particular, they're going to be less than 1. So at a minimum, this function must not go below this line. So that's one part of this. The other part says that the derivative can't be larger than 4. It could equal. So I mean, technically I could shade that in, but I don't want to. And this morning I didn't shade it in, and I kind of thought I should, so maybe I should. No, not shade it in, I mean not do a dotted line, because a dotted line would suggest that we're not including 1. Yeah, let's just leave it like this. The derivative is also bounded by 4. So we take this line with slope 4. This function isn't going to be able to go above that line because its derivative would be larger than 4. So this function must exist between these two dotted lines, and it must go through this point. Now, there technically are further restrictions on what the function can be inside these restrictions given by this, but all we want here is bounds on f of 6. So here's 6, line x equals 6. The largest the function can be is up here if the derivative is always equal to 4. The smallest the function can be is down here if the derivative is always equal to 1 inside that interval. So we need to find these y values. Now, how are we going to, well, any questions so far? We need these y values. You could do a slope or an equation for a line thing. I think an easier way to do it is just to start here and observe. We're traveling, well, and to start here and use a rise over run type argument. So here, the horizontal distance is 5 units. The slope is 1. So if you go over 5 units with a slope of 1, you also have to go up 5 units. So we'd start at 2, up 5 units, gives us 7. Similarly, for the next one, it has a slope of 4. So in 5 units, it's going to have to go up, in 5 horizontal units, it's going to have to go up 20 units, because 20 divided by this 5 would give us the slope of 4. Starting at 2, going up 20 gives us 22. I'll just note this comes from 2 plus 5 horizontal units times slope of 1. And here we have starting at 2 again, plus 5 horizontal units and a slope of 4. Let me put the camera up a little. So this gives us, I guess I should write a concluding sentence. It says what are the maximum minimum f of 6 can be. So I'll just say, so f of 6 is larger than 7 or equal to 7 and less than or equal to 22. Any questions about this one?
Just for like exam purposes, if we had used like y equals mx plus b and used the given values and plugged it into that to find our answer, would you have seen that as an acceptable method, or would you prefer like this?
Yeah, you could. It would probably be a little more work to find equations for those lines, although I would say point slope form would be a little faster because you do have the point 1, 2, and you have the slopes. But yeah, if you found equations for the lines, that would be fine also. Any other questions? So this is way 1. I'll show a second way. The second way I personally think is harder, but it might look easier. It uses the mean value theorem directly. Second way is probably more of an expected way unless you use the hint. So way 2. Well, we're going to use the mean value theorem. And I'm going to write the mean value theorem down here. There's a value at c where f prime of c is the slope of the other line. But here we're looking at 1 through 6. And we're going to use the fact that the derivative is bounded on a general C value. So the mean value theorem, its statement applies to a point within an interval. But you could change A and B around and change this secant line around. And because of that, you can extend the mean value theorem from applying to a point to actually applying to an entire interval. Now, what does that all mean? I have a different marker. I'm going to use this one right now. That means, what are our numbers? F of 1 equals 2, and the derivative is bounded by 4. So we'll take the one side of the mean value theorem. So we have the right side of the equation, f of 6 minus f of 1. Well, f of 1 is 2. 6 minus 1 is 5. That's the one side. The other side tells us that the derivative, I'm going to use x in a more general sense here instead of c. But the mean value theorem tells us the derivative on this interval is going to equal that. Well, the derivative at each point in the interval will look like that. And it depends on what f of 6 is, because f of 6 here isn't necessarily constant. What we can do here is solve for f of 6. How do we solve for f of 6? Well, multiply by 5, add 2, and we've solved for f of 6. Well, now we just use our bounds. F prime x is between 1 and 4. So the smallest this can be is when f prime is 1. The largest this can be is when f prime is 4. So how should I write that? F of 6, the smallest it can be is when the derivative is 1, gives 7, and the largest it can be is when the derivative is 4. And the derivative is 4. So that gives us the same bounds. And it actually gives the same bounds with the same equations, which is not a coincidence. Any questions about number 2? Is anybody having trouble seeing this board? It's a little dark in here right now. Actually, I'm going to turn the light on and see if that. Oh, there's no glare. No, I actually. Sorry, I don't want the light on because. Well, I don't want it too bright. So any questions about 1 or 2? The mean value theorem, very important theorem in calculus. It allows you to determine a lot of behavior about the derivative on intervals. And we used that to get several results in the lecture 10.2 on graphing. And all of those results for the first half hour of the graphing lecture can be summarized as a graph can be pieced together. Well, a sketch of a graph is a bunch of these put together. And we can easily describe each of these pieces of graphs with the first and second derivatives. And all of that is a result of the mean value theorem. So let's do these last two. 3a. Sketch a graph of this function f of x is 2, -15, +9, -x cubed. So this graphing method, as I mentioned in the email, does apply to any function. On a test, it'll be a polynomial type equation. Like, well, on the next test, it'll be more like part A. On the final, it could be like part A or part B, something like that. So here we're gonna need the first derivative. We need where it's 0, and we can use that to find where the function is increasing and where the function is decreasing. And then we'll need the second derivative where that's 0, and we can use that to find where the function is concave up and where it's concave down. So we'll start with the first derivative. So here we have a negative 15, positive 18x, and a negative 3x squared. We need where this is 0. So I'm going to pull out a negative 3. I'm also going to write this term first. So you get x squared, pull a negative 3 off that, you have a negative 6. And an x, pull a negative 3 off that, you have a positive 5. We need where this is 0. That does factor into x. 5 and 1 make 5. 5 and 1 make 6. The negatives work out. So x minus 1, x minus 5. And this is 0 when x equals 1 or when x equals 5. So we have where the derivative is 0. I'll do it like that. So I'm not going to be able to fit all of this work on one board. So I will have to erase something eventually. So we have that the derivative is 0 when x is 1 or x equals 5. In general, for non-polynomials, you would also have to find where it's undefined, but this is a polynomial, so it's always defined. And now we use 1 and 5 to break the real number lineup, and the resulting subintervals. Well, on the resulting subintervals, the sign of the derivative determines whether the function is increasing or decreasing. So we need the derivative evaluated somewhere in this interval. I'll choose 0. And the sign of that will tell us behavior about the original function. So we don't need this actual f prime of 0 value. And with 0, it's easy enough to find. It's just negative 15. But I'll just say it is a negative number. And here in 1 to 5, we'll pick a value. I'll pick 3, I guess, right in the middle. And we only need the sign. So you could substitute it up here in that equation, but I'm going to use this nice factored form because it makes it clear how we can count the signs. So we have substituting negative 3, negative times positive times negative. 2 negatives make a positive. And over here, f prime, we'll say 6. At 6, we have a negative, we have a positive, we have a positive, which makes 1 negative. Any questions about what we have so far? Oh, I thought there was something shining on the screen. It's the cursor. There's a dot right here on my computer, but I thought there was some weird light shining, but it's just the cursor on my computer. Any questions about getting here? Okay. So the sign of the derivative determines whether the function is increasing or decreasing on these intervals. First derivative is negative. The function is decreasing negative infinity to 1. First derivative is positive. The original function is increasing on 1 to 5. And over here it's negative. So the function is decreasing 5 to infinity. And with all of this analysis that we're doing, we're using behavior of the derivatives to determine, well, we're using information from the derivatives to determine the behavior of our original function. So the goal here is to reach conclusions about the original function using the derivatives. But now we need to do this for second derivative to determine concavity. Second derivative is 18 minus 6x. And this is 0 when x equals 3. 3 times 6 is 18. Okay, I just heard beeping. Maybe that is someone. So here we have the second derivative is 0 and x equals 3. We'll block off 3 on our real number line. We have these two intervals to consider, and the sign of the second derivative will allow us to determine the concavity of the original function. So here, a number on this side of 3, I'll pick 0. Here, a number on that side of 3, I'll pick 4. Second derivative at 0 is positive. Second derivative at 4, 18 minus 24 is negative. Oh, sorry, that's coming from outside my office. Okay. I was thinking my phone was beeping or something. My computer was beeping. Where were we? So the sign of the second derivative determines concavity. Where the second derivative is positive, the original function is concave up. Where the second derivative is negative, the original function is concave down. Any questions about finding these two things? Okay. So once we have these, we're in a position to piece together our graph. And I'm debating where I want to write it. I'll do it like this. So I'll erase this and use that. I guess I can leave that there in case people are writing that. Let's draw an XY plane. Let's move the y-axis over because our values are 1, 3, and 5. Or no, the y-axis. I sometimes get x and y-axis confused. 1, 3, and 5. So the calculus determines a lot about the function. But one thing the calculus doesn't determine is whether the function is down here or up here. Now, a function down here, you can translate that up, and the calculus would be the same. So we need to determine the height of our curve. And the easiest way to do that is to use the y-intercept, because that's the easiest point to find, usually. So here, our original function is erased. I think it was 2. Yes, the y-intercept for our function is 2. So we have the point 0, 2. I'll label that down here. And now we need to piece together curves. Looking at the chopped off subintervals of the x-axis. First, we have -∞ to 1. Here, the function is decreasing and concave up, decreasing and concave up, and it goes through this point. Will look like that. That piece is decreasing, it's going down, and it's concave up because the caved in portion is pointing generally upward. Any questions about that first piece? Okay. So next we have 1 to 3. On 1 to 3, function is increasing and it's still concave up. So it's going to start going up, but the caved in portion is still going to go up. So on 1 to 3, it's going up, so it's increasing. The caved in portion is pointing upward. On 3 to 5, the function is increasing, so it's still going up, but now it's concave down. So we need to keep going up, but we need to have the caved in portion pointing downward. And on 5 to infinity, our last interval, it's decreasing and concave down. So that'll look like that. Any questions about this sketch? So the directions say label the local maximum, local minimum inflection points, y-intercept if they exist. So here we do have this local minimum. It doesn't say use an ordered pair, so you don't have to find the ordered pair. Here, well, we have a local minimum there. You can see that on the graph, but you could also see it just from this, because it's a continuous function, and before 1, it's decreasing. After 1, it's increasing. So that gives you a local minimum there. Or you could see it on the graph. And similarly, at 5, it goes from increasing to decreasing, so we have a local maximum. And at 3, our concavity changes and it's continuous, so that gives us an inflection point. So any questions about 1A? Now, if you did find the ordered pairs for 1, what would you get? You'd get 1 and -7. So this does technically go below the x-axis, but you know, this is just a sketch. I'm not too concerned with that. You know, the easiest way around that is to just say that this is not the line y equals 0. You can say this is the line y equals like -10 or something. Or if you don't even want to find that, you know it's negative, say y equals 1,000, -1,000. But you don't have to worry about that. You know, if you ever are asked to find these ordered pairs and your sketch is above the x-axis, you know, then you would know, well, this does get lifted down a little more, this piece at least. But don't worry about that. You worry more about the calculus and the intercept. So any questions about A? 3A. Okay, so 3B, a little more complicated because the derivative computations are a little more complicated. But the first and second derivative analysis, the logic behind it is still the same. So here we have 3 and B. F of x is 4 minus x squared to the 5th. So again, we're going to need the first derivative where it's 0, second derivative where it's 0, and we'll go from there. So first derivative, well, right here, notice, and we are going to need a chain rule computation for this first derivative. We have a function to the 5th, derivative is 5 of them to the 4th, and then times the derivative of 4 minus x squared, which is -2x. And we're going to want to set this equal to 0, so I'm just going to put the, I'm just going to rearrange it and put the 5 and the 2 together. So 5 and 2 and negative make -10. I'll put the x out front. And then 4 minus x squared to the 4th is still there. Now, we need where this is 0. So it equals 0 when the first thing is 0 or when the second thing is 0. 10x is 0 when x equals 0. Same with -10x. 4 minus x squared is 0 when x squared equals 4. which gives us positive or negative 2. Any questions about the derivative, first derivative? Okay, so now we're going to do our sign analysis. We have 2, -2, and 0. So we need the sign of the derivative over here. I'll pick -3. We need the sign of the derivative in here. I'll pick -1. The sign of the derivative here. I'll pick 1. The sign of the derivative here. I'll pick 3. And notice here, this quantity to the 4th, well, it's raised to the 4th. So it's always, this piece at least, is always going to be positive, because raising anything to the 4th gives you a positive. So the sign of the first derivative is going to be determined by this -10x. And -10x at x equals 3 is negative, at x equals 1 is negative, and -1, -10, -1 makes a positive, and at -3 makes it a positive as well. So you could make that slight shortcut observation, or you could substitute these numbers and you'd get the same thing. So for -1, you would get -10 times -1, so positive, times 4 minus 1, all to the 4th, which is positive. And similarly for the others, this one you'd get the negative, well, this one and this one you'd get a negative to the 4th, which is positive. But the sign of the first derivative tells us where the function is increasing or decreasing. So here, first derivative is positive, function is increasing. Here, the first derivative is positive, function is increasing. Here, the first derivative is negative, function is decreasing. And there, the function is also decreasing. Any questions about first derivative and what we did with that? Okay, so now we have to do the same thing with the second derivative. And the second derivative is much less pleasant to deal with, because notice this first derivative has 2 different things with x's multiplied together. So to take the second derivative, we're going to need a product rule. So let's do that. Derivative of -10x is -10 times the second plus the second, or derivative of the first times the second plus the first, so -10x times the derivative of the second. So the derivative of the second, again, is going to have a chain rule, because we have 4 minus x squared all to the 4th. So that gives us 4 of them to the 3rd times the derivative of this inside. So for this product rule, we have derivative of the first times the second plus the first, and the derivative of the second like that. Any questions about just finding the second derivative? And finding where it's 0 is another chore, but any questions about where this came from? Okay, so now we need to find where it's 0. Before doing anything, I'm just going to combine all these numbers and these x's over here. So we have a 10, a 4, and a 2. They make an 80. The negatives make a positive, so we have positive 80. We have an x, we have another x, that's two x's, and we have this thing to the third. So we just combined everything on that second term, and now you could, from right here, set it equal to 0 and solve. I'm going to factor it instead first. So how can we factor this? I'm thinking about where I want to write this and if it'll fit on the bottom of the board. Well, I'm going to go to the top of the board. So I'm going to erase this first derivative stuff. So how can we factor this? Well, we have these two different pieces. What do they have in common? Well, they both have a 10. What else do they have in common? Well, they have 3 4 minus x squared. So we can pull off a 10, we can pull off 3 4 minus x squared. And what are we left with? Well, we take the 10 off of this, we have a negative. We take 3 of those 4 minus x squareds off of that, we're left with 1 of those 4 minus x squareds. Take a 10 off of this, you have an 8. Take 3 4 minus x squared, well, you take all 3 of them, but you still have that x squared. So we pulled off a 10, we pulled off 3 4 minus x squared, and we were left with this. And what's inside those brackets does simplify a little because, you know, this makes a positive x squared, negative 4, positive x squared and 8x squared gives you 9x squared, and then there's a negative 4. And when perfect squares show up, that's usually a good sign. So any questions about finding this simplified form of the second derivative, which we're going to now set equal to 0? So any questions about finding that? Okay. So we want where this is 0, where it's undefined. It's never undefined. Where is it 0? Well, it's 0 when 10 equals 0. That never happens. It's 0 when x squared equals 4. That can happen. It's 0 when 9x squared equals 4. Where is 9x squared equal to 4? Well, when x is 2/3 or negative 2/3. Why is that? Well, we set 9x squared minus 4 equal to 0. So you get x squared is 4/9. And that gives you x is 2/3 or negative 2/3. And all of that work was so that we could chop up a number line. So any questions about finding where that's 0? So now, remember, this is the second derivative. The sign of the second derivative tells us about the concavity of the original function. So the second derivative over here, well, we'll pick negative 3. In here, I'll pick negative 1. That's the most convenient number in there. In here, I'll pick 0. In here, I'll pick positive 1. And over here, I'll pick 3. And there are actually a couple shortcut observations you could make in this computation because all of these x's are squared. So, you know, what happens over here happens over there. But I'll go through all 5 of these in case, you know, that observation And I'm not sure if I would make that observation until after going through all five. So f second prime at 3. Well, we have a 10, which is positive. 4 minus 9 is negative. Negative cubed is negative. So we have positive times negative. Here we have 9 times another 9 minus a 4. That's going to be positive. So we have what? Positive, negative, positive gives us a negative. At 1, we have positive, positive, positive. Which is positive. At 0, positive, positive, negative. At negative 1, and negative 1, it'll be the same as this. Why? Well, we have a positive, and a positive, which is positive. And at negative 3, we have a positive, a negative to the third, so negative, so positive, negative, and positive. Makes it negative. Where the second derivative is positive, the function's concave up. Where the second derivative is negative, the function's concave down. So any questions about finding this, well, about the second derivative analysis? Okay, so now we have to sketch the curve. Y-intercept here, I should have seen ahead and drawn that somewhere else. Is anybody still writing this number line or anything on it? Because I would like to erase it to draw this function. So is anybody still drawing it? Okay, I'll take that as a no. I need that lower. So this function has y-intercept. So the y-intercept 4 to the 5th. You could leave it as 4 to the 5th if you want. That's good line. You could leave it as 4 to the 5th, as you say 0, 4 to the 5th. I've seen the powers of 2 enough in the last 15 years that I know that one, I guess. So the y-intercept is 0, 4 to the 5th, 0, 2 to the 10th, 0, 1024. But now we need to divide up our x-axis. So we have relevant values of -2, -2/3, 0, 2/3, and 2. And to do this one, I'm gonna, instead of starting over here, I'm gonna start at 0. So I'll start at 0, because 0 is one of our relevant values. And I'll go in the positive direction, then I'll do the other way. From 0 to 2/3, the function is concave down and decreasing. Concave down and decreasing, it starts at this point, it'll go somewhere over here. Concave down and decreasing looks like that. And okay, 2/3 is now over there. Any questions about that first piece? I'm probably going to wind up moving 2 also. 2/3 to 2, the function is now concave up, but it's still decreasing. So it'll switch to one of those. I guess two is okay where it is. And we're going to have to label local max and local minimum inflection points. So I'm just going to label this inflection point right now, because concavity did change that, and it's continuous. From 2 to infinity, the function is still decreasing, but it's going back to being concave down. Giving us another inflection point. And that one goes to infinity, so I'll throw an arrow on it. Any questions about that half of the graph? Okay, so the other half, on -2/3 to 0, the function is increasing, but it's still concave down. So it's increasing and concave down until it gets to that point, starting at -2/3. So we'll put an increasing and concave down piece. From -2 to -3, the function is increasing and concave up. So we'll put an increasing and concave up piece. It gives us that inflection point. And on -infinity to -2, increasing concave down, which would give us a piece like that. And another inflection point. Let's make that in half. Okay, that didn't work. So any questions about this graph? This also does give a local maximum. So any questions about this graph? This function does have no local minimum, in case you were wondering. It also has no absolute minimum. This doesn't ask about absolute minimum. So any questions about this one? Let's label this f of x. Now again, not drawn to scale. I guess this point goes through the x-axis. That's okay. So I did send an email with some exam information yesterday, I think it was. So L'Hopital's rule will not be on this test. It will be on the final. The reason I didn't put it on this test, there were a bunch of mistakes on 4B on the last homework assignment. And I did something where there are a bunch of mistakes, and I just did the grading, a week before the test. I don't think that's really enough time to, for that many people to, look it over. So I'll push all of L'Hopital's rule off until the final. Between exam 2 and the final, I will go over a problem like 4B on the homework in detail. I'll go through an explanation in one of these at the end if there's time, which there should be for one of them. But the test, it's mostly written. Several derivative questions. Number 1 is going to be, of the 50 points, probably 20 or 25 points, do some derivative computations. So chain rule, implicit differentiation, logarithmic differentiation will all be tested. There will be a related rates, linear approximation, differentials, maybe both. Extreme value theorem, sketch of a graph. The sketch of the graph, for a 1-hour test, a problem like 3B on this worksheet, that would, if I put one like 3B on the test, I'd have to remove 1 or 2 other topics. So on a 60-minute test, a sketch of a graph would work out more like 3A than 3B. But the final exam is a 3-hour test, so there is a little more that can be asked during that. Oh, we also covered some like velocity acceleration. We saw that in its own lecture on rates of change during that week, but we also saw one of those during the mean value theorem. So, something like that could show up. But do remember L'Hopital's rule will not be tested, so don't in the next 5 days spend much time on that. Are there any questions? Okay, well, now I'll end this now. They're about 15 minutes. So if you do have any questions, I'll leave this link up for the next 15 minutes. I do have to go at 3:15 though. So if you do have questions, you can stay and ask them. If not, I hope you enjoy your weekend and find some time to study for this test.
Thank you.